Good morning, everyone. My name is Robert Carr from eWater, and welcome to our webcast this morning on modelling groundwater-surface water interactions using source. I've got the pleasant job of just doing the quick introductions, and then I'll hand over to Rachel and Daniel to take it through. Rachel is a hydrologist with eWater and is in the final stages of her PhD on
The broadcast is now starting. All attendees are in listen-only mode.
National University. We also have Dr. Daniel Partington with us. Daniel is a postdoc fellow at Flinders University and has been working on a model intercomparison project comparing different scales of groundwater surface water interaction tools. So the purpose of this is really to explore the different scales of tools in source for dealing with groundwater surface water interaction, from simple lumped conceptual tools right through to 3D integration with ModFlow. The important issue here is that we are not modelling groundwater for the sake of groundwater resource assessments, etc. This is really to focus on different scales of evaluating the influence of groundwater processes on river flows. So the outcome here is better definition of groundwater contribution to river flows. Of course, the ultimate tool is ModFlow or FeeFlow or other 3D groundwater models which can be connected to source, but the focus here is on the appropriate scales depending on data and complexity of groundwater components on river flows. This is a little bit of a precursor into our upcoming groundwater surface water course that we're holding in Adelaide, and Rachel and Daniel will tell you more about that later. So onward, and thanks for joining us, and I'll hand over to Rachel to take it from here.
Thanks, Robert. I'm going to be giving a brief overview of Source's groundwater modelling capabilities, and then I'm going to demonstrate the new groundwater heads model. Okay, Source has 5 scales of groundwater modelling available. The first is to lump groundwater into our rainfall runoff models as a loss or a gain. This is okay for rainfall generated base flow, but obviously we can't measure the impacts of things like pumping. The second approach is to use the perfect groundwater lag model. This is a rainfall runoff model that has a simple delay-based component added, and this model simulates the movement of groundwater through the aquifer, and we can also look at the impacts of things like pumping. Sorry, we have just one moment. Can people hear our presentation? Just type in on the questions box to let us know. Great, okay, thank you. We'll continue with the presentation. Groundwater lag is suitable for upland river catchments and unregulated systems. It's not suitable for modelling the detailed recharge-discharge relationships on a river reach. The third scale of modelling that we have is the Groundwater-Surface Water Interaction tool, or the Analytical groundwater model. This model is a reach scale model that calculates the exchange of water between the river and the underlying aquifer. It's suitable for modelling the long-term impacts of water resource policy on system storages, flows and water shares in regulated rivers. To look at this model in a little bit more detail, the model is based on analytical and empirical solutions to the groundwater flow equations, and it includes processes like pumping, overbank flow and the bank storage discharge relationships, evaporation, floodplain infiltration from diffuse and irrigation sources, and it's suitable for unsaturated and saturated connections. It also includes a component enabling you to model constituents like salinity. The model estimates the surface water groundwater exchange fluxes from each of these individual processes and then uses superposition to evaluate the overall flux. So this is a really useful tool for modelling the effects of pumping and recharge, particularly when there isn't much data or you don't want to build a full-blown 3D groundwater flow model. However, the model does have some drawbacks, and one of those is that if you have time varying inputs, the model runtime can slow, and this is because each time you change your pumping rate, for example, then the model spawns a new solution to the equations. So obviously if you have a lot of time varying inputs, the model then slows down. The second issue is that in its current form it doesn't display groundwater heads, and if you want to be able to calibrate your model to observed heads, obviously that's a concern. So because of these things, we've also introduced the new groundwater head model, which is also known as the numerical groundwater model. So this model is designed to address some of the limitations of the analytical model, and it duplicates a lot of the same functionality but also extends it, and that's obviously what I'm going to be talking about primarily today. The final model is a full-blown mod flow connection, which enables a runtime linkage between mod flow and source. So the mod flow connection needs work and it isn't available in the latest versions of source. The items 1, 2 and 3 are available in the public version of source, and item 4, the head model, is in the public beta. So next I'm just going to give a brief introduction to the structure of the numerical groundwater model. It's a one-dimensional finite difference solver, and structurally the user divides the river link into a number of cross-sections, and then the 1D solver estimates given the heads in each cross-section, estimates the fluxes between them and the river link. The model also includes no flow boundaries on the right bank and also on the base aquifer basement. In this diagram here I've only shown the right bank, but obviously the model has left and right banks. To make the diagram clearer, I've only included one. A key difference between the numerical model and the analytical solution is that the numerical model attempts to calculates the soil moisture in the unsaturated zone. For those who are interested, it does this using an approach that's based on the mean-Larsen formulation of the Green-Ampt equations. So this enables the model to simulate diffuse recharge from processes like rainfall and also ponded recharge, or from flooding or overbank flows. The model, similarly to the analytical approach, also includes pumping and injection bores and processes of evaporation. Next I'm going to go to a demonstration of the model, and the first project that I wanted to show is just a very simple example, and I'm going to demonstrate that the numerical model is equivalent to the analytical model. So here I've actually already created a very simple project where we have a constant inflow of 500 megalitres a day, and then we have a river reach where I've added the saturated analytical groundwater model. I'm not going to go into the details of this because it's an existing feature of source. I've set some parameters for the aquifer properties, and I've also added one pump This pump turns on after a few years, oscillates on and off for a while, turns off and then turns on again, and I've defined it using a function. The pump is located 1,000 meters from the riverbank. So what I'm going to do now is I'm going to create an equivalent numerical model. And so I'll just rename my new link to Numerical Model. Now, if you're creating this model from scratch, normally you'd need to right-click on the link and change the routing type to storage routing, but we've already done this for this copied and pasted version. We're going to go into the groundwater menu, delete our analytical model, and create the new saturated numerical groundwater model. The first pane here is similar parameters to what were in the analytical model. So we're just going to set equivalent model values to what I used there. I just want to note that this is a synthetic example, so it's not supposed to represent physically meaningful parameters in any way. The second pane that we have here are mainly the settings for the finite difference solver. So we're going to choose the number of divisions per each bank of the river, and we're going to set an aquifer floor depth of 20 meters or minus 20 meters in our coordinate system. Here we can choose the initial heights for the groundwater table, and we're going to set it to the height of this river at time t equals 0. This third pane deals with some of the parameters for the unsaturated zone. We'll use an initial soil moisture of 20%. We want our saturated soil moisture to be greater than our initial one, so I'll put 40%. We'll set saturated vertical hydraulic conductivity of 1 meter per day, and the average suction, which is the suction at the wetting front, we're just going to use 0.1 millimeters. It doesn't actually matter for this example. Now, one of the key features of this new numerical groundwater model is that we have the concept of a cross-section, and this defines the geometry of the riverbed and also of the floodplain. I've already loaded one in this project, so I've just opened it there. We've defined the left and right bank positions of the river, and we can see we just have a very broad, flat floodplain. The useful feature is that we can now create a rating curve from that cross-section. So I've right-clicked on rating curve, add from cross-section, and I'll select the one that we use for the groundwater model, and we have a rating curve created. And of course we'll want that for moving between stage or river stage and flow. Finally, we want to add a pump, so we right-click on the model, select Add Pump, and we'll use the same pump as we had for the analytical model. Now I'm just going to set our recorders, and we'll just do one recorder, which is the groundwater flux, and that's the flux between the aquifer and the river. And now I'm just going to run these two models so we can compare the solutions. We would hope that the numerical model is identical to the analytical model, and that's what we're going to show. The accuracy of the numerical model increases depending on the number of cross-sections that you define. I have made one mistake, which is that I forgot to define the position of the groundwater pump, which needs to be at 1 kilometre from the river. I'm going to put it on the right bank, which is, so 1,000 metres from the right bank is at a distance of 6,420 metres in total. So now I'll simulate that again, and the results should be more like what we were expecting to see. So let's look at our new results. And I'm sorry, I've reversed the the numbers in my pump position again. So I probably won't go through simulating that, but I've put it 100. I put it at 6420 instead of 6240. So apologies for that. But normally the two groundwater fluxes between the aquifer and the river would be identical up until this point here. Now this is where in the numerical model the aquifer has become dry. So the groundwater head has reached the basement. The analytical model has an infinite aquifer. So the groundwater flux continues to increase at that point. So that should be the only difference between the two of them. For interest, here is a plot of the pump rate. As you can see, it does nothing for the first 10 years and then it oscillates year on, year off for another 40 years, turns off and then turns on again at a constant rate. And that creates the oscillations and rises and declines that you see in the flux. Now I'm going to move to another model that I've already prepared, and this model demonstrates some of the the new features in the numerical groundwater model. The first thing is that we can now add observation bores. And so the numerical model calculates the groundwater head in every cell, and I've already added 3 observation bores here. One is located directly on our pump, one is located on the riverbank, and one is located far from the river on the other side of the pump. And these observation bores enable us to look at the groundwater heads at that location as well as some other properties. So opening up the results of that model, which I've already simulated, sorry, we'll rerun that one. We still want to use that constant inflow of 500 megalitres per day. So we'll just run that one again. And now we have our groundwater flux, and here I've defined my model correctly, so we actually have the analytical and groundwater models combined, and you can see that they are indeed identical. But we can also see the groundwater head for the numerical model. The green line here shows the river stage, which is constant because we have a constant inflow. The blue line is the head at the position of the pump. The red line is the groundwater head close to the riverbank, and you can see it's much less, it receives much more recharge as you would expect, although it is slightly impacted by the pumping. And the orange line shows the groundwater head at the location that's far from the river, and obviously it receives less recharge from the river, so the heads show a greater decline. So that's one of the useful new features of the numerical model. The second thing that I wanted to look at, which is what I had enabled before, is the processes of overbank flow. So I'll open up my streamflow and change our input streamflow from a constant value to a function which just sends a couple of flood pulses down the river. Now this isn't a realistic model, so it's actually 2-year-long floods. We'll have a look at the impact of that on the simulated heads in the numerical model. This is the impact on the fluxes, and then we click on the heads graph, and we can see we have our first little flood here and the corresponding spike in the bore that's located near the river, and we have our second bigger flood here, and there's quite a large spike in the aquifer, and that's representing both the head-based exchange between the aquifer and the river and also the ponded infiltration. Finally, we have a few other tools available. We have injection bores. Now that's just the opposite of a pump, and it allows you to inject water into the aquifer. I won't demonstrate that one today. We also have two types of diffuse sources. The diffuse source is applied to the ground surface, so you might use that for estimating infiltration from rainfall. And the direct diffuse source is applied directly to the aquifer. So if you have a rainfall runoff model, for example, and you've already calculated groundwater recharge, you just want to apply it directly to the aquifer, then you'd use that one. So I'll disable that. I've actually already created one, which I'll enable now. And you can see we can define a start and end distance for the diffuse source, which is obviously of interest if you want to look at irrigation. And we've set a constant value of 0.1 millimeters per day. So now that's enabled, and we can simulate our model again, and we would expect to see a corresponding rise in our groundwater heads. The final tool that I'll demonstrate today is the evaporation. And the impact of that on the unsaturated zone and the groundwater. So as you can see, I haven't turned off the stream flow. We have a rise in the groundwater table above the river stage height due to the impact of the diffuse source, and if we look at the flux, we can see a decline in the flux, and the flux is in terms of the aquifer. So a negative value means that the aquifer is losing water to the river. The very final feature that I wanted to talk about today is evaporation. Here we're just, the settings that we want to set here are, we're just going to use an input depth and an extinction depth of 10 meters, so evaporation won't occur at depths below 10 meters. And previously we had no evaporation being applied. We're just going to use a very simple value of 1 millimeter a day and simulate the model again. So this one is of interest because we can see the impact of including the unsaturated zone on our calculations. So I'll just bring that up again. What we can see here is that initially we have a small rise, which was exactly the same as the previous graph. And what's happening here is evaporation is depleting soil moisture in the unsaturated zone, but it's not actually affecting the groundwater table. Then, at the point where my cursor is, this is where the soil moisture in the unsaturated zone has been depleted and we're starting to impact the groundwater head. So that's the final feature that I wanted to demonstrate in the numerical groundwater model. Next we're going to hand over yes, diffuse infiltration. So the question is, can diffuse infiltration be used for infiltration from irrigation? And the answer is yes. You can inject that directly to the aquifer via the direct diffuse source. And you can choose the spatial domain over which you inject that infiltration as well. So now we're handing over to Daniel Partington from Flinders University. He's going to be talking about some research that he's doing on an intermodal comparison using source. This work is still ongoing, but the results are going to be really interesting in terms of how far we can push the simple analytical and numerical tools available in source in modelling an aquifer, and he'll talk about that in more detail.
Okay, thanks Rachel. So as I said, I'm a researcher in the National Centre for Groundwater Research and Training, and I just want to give a little flavour today of what I'll be presenting in April. So to give you some context of why I'm interested in source and been using it, I've been working on a project which is essentially a model comparison that considers the surface water groundwater exchange in some very different models. So we have the models that have a source, ModFlow, which is the 3D finite difference groundwater model from the USGS, and a more full-blown, fully integrated numerical model, hydrogeosphere. So they're all fairly different models, and the motivation for this research, I guess, comes back to how we manage our water resources. So we have some bigger picture issues in terms of regional water balances and looking at our whole systems, how we allocate these things. We have quite a lot of anthropogenic forcing on these systems, but there's also the smaller scale that is of interest too, where we are trying to understand in more detail the processes that are occurring and the dynamics of these processes. And a common thread between all these problems, though, is that we need to know something about this surface water groundwater exchange, which means using some sort of model. So the way we do this is we create a model either of our stream or of our groundwater system, and there's lots of different models available. For example, we can have a very complex full dynamic wave to simulate our stream water. We can use a less complex diffusion wave, and even more we can shift towards the lumped conceptual versions. And then similarly with groundwater, we can have a very complex 3D variably saturated numerical models, or we can use simpler analytical models like what is currently in source. And with both these models, we then need to calculate some exchange, and that's, I guess, where I'm quite interested. So in terms of quantifying this exchange between our streams and aquifers. So in the work I've been doing, there are some broad points of comparison with some quite subjective things and some other more rigorous and informative comparisons. So just to give you an idea of what I've looked at how easy it is to set up the model. So with source, we have a GUI, and it's fairly nice, and it's a lot easier than, for example, using something like ModFlow or hydrogeosphere, where you are requiring to write text files to set up your model, and you're having to deal with perhaps more complex data sets. The knowledge and training that you need to use these models is also, for the complex numerical ones, is a lot more than what is required for something like source. There's obviously different data requirements because the models have different focuses. Source has perhaps more of a surface water focus, and it uses things like that analytical groundwater model to give a better understanding of the unaccounted losses, which is quite useful. And but in our full integrated models or ModFlow, we need to know a lot more about this characterization of the subsurface and trying to represent that explicitly. So there's a lot more that's required there. But sometimes there's crossover, and there's some stark differences as well. We also have the process representation, so that goes back to that slide earlier, and in the different types of models we use in terms of whether they're 1D, 2D, analytical, numerical, steady state, or transient. And so we also have different types of feedback, the way these different models talk to each other. So we can have sequential coupling of the models where we solve for one, and so we might solve for how much groundwater is discharging stream, pass that to the stream model, solve the next part of the stream model, and then there may be some feedback or not between the two. And there's also iterative methods for doing this, and then in something like hydrogeosphere we have it's implicit, so you're solving one set of equations, so you don't have so you capture that quite well. The different models have different assumptions, which also relates to the process representation in terms of how we simplify the system so that we can model it. And lastly, we have the runtime and calibration uncertainty. This is where source does extremely well because the models are very fast to run, so we can do all types of scenario analysis. We can do a lot of uncertainty analysis. It's easy to run these models many times, to use MCMC and other approaches. In something like hydrogeosphere, this is quite difficult because the models can actually take they can take days to weeks sometimes to run. So certainly the Monte Carlo stuff is very, very difficult to do. So these are sorts of things I've looked at in these different types of models in broad, as broad points of comparison, but more specifically, an interest is how we actually, from what comes from these models, what is the surface water groundwater exchange for different types of scenarios in terms of whether a stream is gaining or losing, or whether that's changing quite a lot, whether there's extra stresses on the aquifer, how it handles that. And also in terms of the surface water, what is, and at a point where a hydrograph is being measured at different points of the model, what the total flow is from the different models, and how much of that flow is derived from groundwater discharging to the stream. So to do this, I've used real catchment as the basis for this research, and the area chosen is the Upper Macquarie River Groundwater Management Area, which is in central New South Wales. So this is it's a very fairly productive alluvial aquifer, it's a narrow alluvial aquifer, and there's quite a lot of pumping that goes on. There's a lot of surface water extraction, and there's some strong surface water groundwater exchanges, which makes this the perfect candidate for building a model and also pushing it in different ways to see how the different models respond in terms of capturing these dynamics. So at the moment, the model looks like this in source. So it's a fairly simple setup. I've got all the gauge stations, and for all the links, there's different ways of implementing, depending on how many the groundwater part, in terms of there's a lot of I guess spatial analysis required with for each of these reaches in terms of the pumps and different rainfall that's falling on the different parts, as well as surface water diversion. So that's implemented, and this is, so in April I'll be presenting this particular model, and I'll go through the details of how I built that. And so finally, yeah, what I'll actually present in April is how I set up the analytical groundwater model for this particular area, how I did the spatial averaging of data to input the links. So for example, I might have had observations, 7 or 8, 4 observations, and how I used that to give a head to get a low flow into the river, and if I had a series of pumps, how I put them in to links as well. And I'll go through how to calibrate the groundwater module parameters using source and test. I'll also present some of the modelling results from this work, and I'll go through those comparison points and show the differences between the surface water groundwater exchange and the stream flow components, so the total stream flow and the base flow. So I hope that gives you a bit of a flavour for what I'll be talking about. So that's about it from me. So just a reminder here that, yeah, so the course is running from the 21st to the 23rd of April, and it will be held in Adelaide. So you can see there's a link there if you want more information and to register for this course. So thank you.
Thanks very much, Dan. Just a note on the link, we'll be providing more information about the course agenda over the next couple of days. So you can go and register now, but if you look in a few days' time, we'll have some more info up there as well. Can you progress to the next slide, please, Daniel?
I only have that last slide.
That's all right. Just to summarise what we've covered today, we've just done a brief overview of the range of groundwater modelling tools available in source, and obviously the appropriate tool depends on the available data and the objectives of your project. We've introduced the new groundwater heads model, which is a simple, flexible tool for modelling surface groundwater interactions. It includes much of the functionality of the analytical model, and we've tested it, and it is around 4 times faster for time varying inputs. Of course, it depends on the how many cross sections you use and how many time varying inputs you have on how much faster. And there's a lot of potential to extend the numerical groundwater model further, and we're actually really interested to hear your feedback on what you might like to see. Finally, the Macquarie case study and the intermodal comparison that Dan's been developing is going to provide some really interesting guidance on practical applications of source, both around the types of surface groundwater interactions that it's suitable for modelling for and how to structure a model of a real system and do the data preparation and those types of things. So thanks very much, everyone. If anyone has any questions, yeah, please just type them in the chat pane on the right. So the first question is that from Joel Hall, is that in the numerical groundwater heads model, can groundwater pumping affect the stage height and flow of the river? It appeared that the stage height was constant even with pumping rates. Yes. So we're going to enable two options. One where the flow, so if we have runoff or other types of interactions that we deduct that from the river. The other option that we're going to have is that we just discard those fluxes. The assumption here is that we have a constant inflow, and also I was showing the flow on the link, and the impacts on the downstream gauge might be different. The second question from Brad Degens, sorry if I pronounced that wrongly. It's just the same question, can the effect of pumping feed back to the river stage along a reach? And the answer is yes. To be honest, I actually need to check what we have enabled in the version that I was showing you. You might have noticed that I was using a nightly beta because we're still testing some of the features, and so yeah, so we'll, the answer is yes, and I can't quite remember what I had enabled in that demonstration. Are there any more questions? And also, if you want to ask a question verbally, you can unmute yourselves on the right-hand pane. Just click on the little icon of the microphone, which will currently have a red line through it. Okay, that seems like it might be it. We'll give a couple more moments if anyone has anything else they wanted to add. Okay, well thanks very much for listening, everyone. Oh, sorry, there is one more question. Can the transmissivity of the river bed be varied from the regional aquifer properties? So currently we don't have the transmissivity of the riverbed enabled. That's a feature that we'll reintroduce. So currently no, but yes, we will be able to do that. And that question was from Brad again. And we have a question from Cameron Dougal. And yes, you can watch this webinar again. We will send it out, so you'll have that available. And yeah, same question from Chaz Egan. Yes, we can. We will be sending a copy of this webinar out, so you can watch it at a later date. Great. Okay, thanks very much for listening, everyone. And I hope to see some of you at the Groundwater Modelling course in April. And we're really interested in feedback on the groundwater